So in this lecture, we'll study the effect of temperature on beta. Beta, as you know, it is given by mu n Cox W by L, where mu n is the mobility of the electron for an NMOS. Cox is the capacitance of the oxide layer, W is the width of the MOSFET, and L is the length of the MOSFET. Okay, so if I assume Cox W and L to be fixed for a particular generation, then my beta, it will be directly proportional to the mobility of the electron. Okay, but what happens to mobility as the temperature increases? As the temperature increases, we say that the mobility, it decreases. Why does it happen? Because whatever will happen to mobility will automatically be reflected in beta. Okay, so because the mobility decreases with an increase in temperature, we say that beta, it will decrease with an increase in temperature. It will start showing the similar behavior. Now, why is it that the mobility, it decreases as we start increasing the temperature? This is because as the temperature increases, the kinetic energy of the electrons or the holes which are present in the specimen, it starts increasing. And as the kinetic energy starts increasing, the electrons and the holes which are present in the semiconductor, they start moving here and there with a greater velocity. Okay, now because they have a good amount of energy present in them, there is a greater chance of scattering or collisions or in other words, we can say that collisions will start, more and more collisions will start taking place. And as these electrons and holes, they collide with one another, they will end up losing their energy that they had gained earlier, and as a result, their velocity or the mobility will decrease. Fine. Now, as the mobility, it decreases because of an increase in temperature, the same, it will be reflected in beta. And we say that for how does this beta, it vary with temperature? It is directly proportional to T raised to power minus 1.5, or it is given by this equation. So as our temperature increases, our beta, it decreases by a factor 1.5. Okay, so now that is how beta, it varies with temperature. Now we'll start with another topic which is called as noise margin. It is a very important concept because it tells us how much noise is allowable at the input of the CMOS inverter, so that there is no change in the output, or the output is not wrongly interpreted. Okay, now okay, what is noise margin? Here I have written the definition. It simply means the allowable noise voltage at the input which has no effect on the output of the device. Okay, or in other words, we can say that what is the extent to which noise can be allowed at the input so that there is no change at the output. How much is the noise that my CMOS, it can tolerate so that the output does not change. It is shown correctly. कितना noise हम लोग input पे tolerate कर सकते हैं so that जो हमारा output है वो wrong वो गलत ना आए, that is called as noise margin. Okay, now if we look at the transfer characteristics of CMOS, they are given by the graph A. Okay, I have already taught you this in the previous lecture, the DC characteristics of the CMOS. Let me zoom in a little bit. Okay, this is my V in and this is my V out. From 0 to VDD by 2, my output, it is here, it is read as high. Okay, it can go up to, it can even go up to VDD, but due to some potential drop, we say it is less than VDD, but still it is high. Okay, after VDD by 2, at VDD by 2, both the CMOS, both the transistors of the CMOS, they are in saturation mode, as you know from the previous lectures. Okay, after VDD by 2, as my input, it exceeds VDD by 2, my output, it will start coming down, and ideally it should go to 0. Okay, this is how the DC transfer characteristic curve of a CMOS looks like. Okay, so this is what I have written over here. I have written everything in this paragraph. Okay, as my say up to my VDD by 2, input is up to VDD by 2, the output is high, and after the input it crosses VDD by 2, the output it becomes low. Okay, ideally what do we say? We say that from 0 to VDD by 2 the output is high, say VDD. Okay, and as V in it exceeds this value VDD by 2, my output it immediately drops to 0. But these are the ideal characteristics of the MOSFET. In a real scenario, these are not possible. Why? Because the slope in this graph it is infinite, and to have an infinite slope that is a little bit difficult. Okay, so we don't have a sharp cutoff at VDD by 2. It's not like कि हमारा जो output है वो VDD by 2 पे abruptly drop हो जाता है to 0, but it starts coming down gradually as is shown in graph C. Okay, now look at this graph C. What is there in graph C? In graph C आपका जब तक input है from 0 to VIL, okay, आपका जो output है it is read as high. Okay, it is either VDD or it is it is some value which is interpreted as high, that is VOH. So VOH is the minimum value, minimum output value जिसको हम लोग क्या assume करते हैं as logic 1. Okay, कहाँ से कहाँ तक? when your input is from 0 to VIL, जब तक आपका input 0 और VIL की range में है तब तक जो हमारा output है it will be either VDD or it will be VOH, and both these logic levels VDD and VOH they are taken as logic 1. Okay, after your input it crosses VIL, okay, then there will be a gradual slope which is shown by this line, and the output it will start decreasing. Okay, and as the input it starts reaching this value VIH, your output it will come down and it will acquire a low level which is VOL, and it can even come, ideally we say that it can come down to 0, but due to some grounding issues it does not come down to perfect 0, but it acquires a low level which is called as VOL. ठीक है, तो सिंपली आप इस ग्राफ से क्या समझ रहे हैं? आप इस ग्राफ से ये समझते हैं कि जब तक इनपुट आपका होगा बिटवीन 0 एंड VIL आपका आउटपुट क्या होगा? इट विल बी हाई, और जो ही आपका आउटपुट इस VIL से एक्सीड हो जाता है देयर इज़ अ डिक्रीज इन द आउटपुट, एंड आफ्टर इट क्रॉसेस दिस लेवल VIH the output it will come to a lower value, to a lower level which is denoted as VOL. Okay, so here I have written what these terms mean. VIL is the low level input corresponding to which we have a high level output, because this is an inverter. Inverter क्या देता है? low level input में वो एक हमें हाई लेवल आउटपुट देता है. तो VIL जब तक आपका लो लेवल इनपुट आपका जब तक VIL तक है, आपका जो आउटपुट है इट विल बी मेंटेन्ड एट and similarly जब तक आपका input level high है, high means VIH which is your high level input, the corresponding output is VOL or the low level output. Okay, now as long as the input it is between 0 and VIL, the output is high, VOH or VDD, and as long as the input is between VIH and VDD, the output is low, that is VOL or 0. Okay, so this is how the actual graph looks like in a practical scenario. Okay, this is the same thing, but यहाँ पर what is the difference between this graph? Here the slope it is sharp. In this graph I've shown that it is not sharp but it is a little bit gradual. Okay, fine. So up to the point when your V in is between this range, your output is in this range, and when your input is in this range, your output is in the range 0 to VOL. As your input is low, in the low range, your output is in the high range, and as your input is in the high range, your output will be in the low range. That is basically what your CMOS does. Okay, now, okay, if you look at this closely, VOH is the minimum high output value, and because VOH is the minimum high output, because the output it can go up to VDD. So but what is the minimum value that we take as high? अगर आप इस ग्राफ पे देखेंगे आपका जो हाईएस्ट वैल्यू है वो क्या हो सकता है, VDD हो सकता है. बट व्हाट इज़ द मिनिमम वैल्यू दैट वी इंटरप्रेट एज हाई, दैट इज़ VOH. बिटवीन VOH एंड VDD कोई भी वैल्यू आप पे आपका आउटपुट आएगा, दैट विल बी इंटरप्रेटेड एज logic 1. Okay, so VOH is the minimum high value. Okay, and then VOL is the maximum low output, because the output can go below to 0. Okay, here is your output VOL. VOL कौन सा वाला लेवल है? VOL वो वाला लेवल है जहाँ तक हम लोग बोलते हैं कि जो आउटपुट है it can be treated as 0. So it is the maximum low output, because the what is the minimum low output? The minimum low output will be 0. From 0 to VOL आपका कोई भी output का value आएगा, so you will take it as logic 0. And what is the maximum level that you can take as the low output? That is your VOL. Okay, similarly VIL is the maximum low input, because the input it can go below to 0. So this is now coming to the input side. Here ये रहा आपका इनपुट. VIL क्या है? VIL वो इनपुट का रेंज है जहाँ तक आपका इनपुट इज़ कंसिडर्ड एज लो. ओके, सो 0 टू VIL हम लोग बोलते हैं जहाँ पर भी आपका इनपुट अगर इफ इट लाइज बिटवीन 0 टू VIL, then at that time the output is considered to be high, because this input is considered to be low. So VIL is the maximum level of low inputs. Okay, and then what will be VIH? VIH, anywhere from VIH to beyond, we say that my input it is high. So VIH is the minimum value of high level input. Okay, so looking again at this graph and defining these voltage values, what is VOH? VOH is the minimum high output. O means output. तो minimum जो आपका output high हो सकता है वो कितना हो सकता है? VOH. VOH से लेकर आपका ऊपर कहीं भी जाएगा up to VDD, it is considered as high. So VOH is the minimum value of output. Okay, VOL क्या हो गया आपका? VOL is the maximum low output. अगर आपका आउटपुट 0 टू VOL कहीं पर भी आएगा तो वी से दैट द आउटपुट इट इज़ लो. सो व्हाट इज maximum allowable low output? That is VOL. Similarly, what is VIL? VIL means VIL is the maximum. Now VIL is on the input side because it has I and L. I means input and L means low. Okay, so this is the maximum value of low level input that your CMOS can have. Okay, so anywhere from 0 to VIL we say that the input is low. Okay, then what is VIH? VIH is the minimum value of the input that is considered to be as high. VIH के beyond आपका अगर input जाएगा then it is considered to be logic 1. So what is the minimum value for high level input? That is VIH. Okay, now this is what I have written in these